A quiet, golden grassland sits within a 750-mile-long scar. A wound so deep it didn't just shake California, it reshaped it. This is the Carrizo Plain, a pull-apart basin formed where the San Andreas Fault stretches and tears the crust through sideways, grinding so powerful it literally repositions landscapes over time. Streams bend like snapped wires. Ridges are sliced with ruler-straight precision. And at Wallace Creek, the ground has been shoved 430 feet sideways, the fingerprint of thousands of years of relentless motion. Before we go any deeper, quick, when you picture earthquake damage, what comes to mind? Cracked roads? Swaying buildings? Or do you imagine the ground itself suddenly sliding past itself like two giant pieces of broken glass? Because that's what the San Andreas actually is. To the west, the Pacific Plate, carrying Los Angeles, drifts northwest at roughly 1.5 inches per year. To the east, the North American Plate resists that motion, the friction locking massive slabs of crust together, until the accumulated stress finally overcomes the resistance. And this grinding doesn't just break rock. It transports entire landscapes. Pinnacles National Park, those towers of volcanic rhyolite, actually formed nearly 200 miles south, then rode the Pacific Plate northwest for 23 million years. But here's the part California doesn't like to think about. The southern section of the San Andreas has been locked for over 300 years, longer than any quiet period in recent geologic history. That's 3 centuries of strain slowly building, millimeter by millimeter, with no release. And the real question isn't what the fault has done. It's what happens when all that stored motion finally tears loose in seconds. Most valleys on Earth are carved by rivers or ice. But this one, it was carved by geometry, an accident of direction. Along the San Andreas, the fault doesn't run straight. It bends just slightly. And at those bends, physics decides the landscape's fate. Where the fault bends inward, the crust is crushed upward into mountains. But where it bends outward, just a few degrees, the ground is literally pulled apart. This is transtension, a sideways tear that creates long, sinking basins. The Carrizo Plain sits in one of these releasing bends, not because water cut it, not because wind hollowed it out, but because 2 slabs of earth misaligned by a fraction of a degree. When the plates slip, even by inches, the ground sags. When they lock for decades, strain builds, bowing the crust downward. With every cycle, the basin stretches wider, quiet, hidden, relentless. And the proof is everywhere once you know what to look for. Sag ponds, small depressions filled with water that form where the crust sags during a slip. Fault-aligned valleys, perfectly straight troughs, impossible to explain through erosion. LiDAR scars, laser maps revealing microscopic tears, invisible from the ground. Sediment cores, layers of ancient lake mud showing this valley didn't exist a few 100,000 years ago. Here's a question for you. If you drilled 100 meters beneath the Carrizo Plain, what would you expect to find first? River gravel or lakebed clay? Because the answer reveals whether this valley was carved by water or by the earth tearing itself apart. And that brings us to the real tension. The same mechanics that created this valley are still operating today, still pulling, still loading the fault like a spring. The San Andreas Fault is always moving, except when it isn't. And that's the part geologists lose sleep over. Most of the fault, especially near Parkfield, creeps along steadily, releasing stress in tiny slips you'll never feel. But the southern section, the one staring straight at Los Angeles, hasn't budged since around 1690. That's not just unusual. It's physically wrong. A fault that should be sliding inches every decade has been locked for more than 3 centuries, building up stress like a metal beam bending underweight. And here's the why behind that lockup. The part most people never hear. Up north, the plates can slide past each other more freely. But as the fault approaches the San Gabriel Mountains, it takes a sharp, unnatural turn. Geologists call this kink the Big Bend. That bend forces the plates into partial head-on collision instead of a clean sideways glide. It acts like a geological brake pad, slowing the fault, jamming it, turning smooth motion into stored, rising tension. Modern GPS stations, bolted deep into bedrock from Bombay Beach to San Bernardino, measure this invisible struggle. Every year, the ground shifts by millimeters, pulled in opposite directions, as if the surface of California is caught in a gigantic rack, stretched in some places, compressed in others. But GPS only tells you what individual points do. To see the whole region deform at once, scientists use InSAR, satellite radar, that measures ground movement from orbit. These images reveal the Mojave Desert and the nearby mountains subtly bowing and flexing, like a trampoline under slow, uneven pressure, and the greatest deformation, right along the lock segment of the San Andreas. But here's the truly unsettling part. Despite all this measured motion, the ground isn't slipping. It's holding everything in, storing stress, microscopically fracturing, preparing. It even shows up in the landscape. Fences slowly bend out of alignment. Road stripes drift. Drainage channels list by fractions of degrees. Changes so subtle you need laser measurements to catch them. Your turn for a guess. If you could hold a chunk of rock from 10 meters below this lock zone, do you think it's A, intact and unchanged, or B, already riddled with microscopic cracks from centuries of tension? Because drill cores pulled from near the fault show the answer. And it is an A. And this leads to the next hard question. How much stress has accumulated? Some models suggest the southern San Andreas is now carrying at least as much strain, and possibly more, than the buildup that preceded its last major rupture more than 300 years ago. This is where the story turns. From slow, patient creation to sudden, catastrophic release. And the moment that release begins, everything changes. For centuries, the southern San Andreas has been wound tight. When it finally gives way, it doesn't begin with a roar. It begins with the failure of a single asperity, a jagged point of rock that has held the plates together longer than the United States has existed. Deep beneath the Salton Sea, where the fault is tangled with active geothermal fields and crossed by a web of intersecting microfaults, that critical point finally snaps. And this is the most dangerous place for such a break, because a rupture that starts here has the longest possible runway to tear northward into the main lock segment. The rupture doesn't move upward or downward. It unzips sideways, racing along the fault at nearly 2 miles per second, faster than a rifle bullet, too fast for the human eye to track, too fast for the human brain to comprehend. The land doesn't lurch at first. It shears, 2 slabs of the continent wrenching past one another after centuries of resistance. 300 years of stored strain convert into explosive motion in less than the time it takes to blink. Elastic waves burst outward, P waves sprinting ahead like messengers, S waves following like a rolling wall of violence. Within seconds, sensors from Bombay Beach to the Cajon Pass spike off the charts. On the surface, the first signs are deceptively small. A ripple in a canal, dust lifting from the desert floor, a fence line shivering out of alignment. Then the ground begins to move sideways, not shaking but sliding, dragging everything on it, trees, roads, power lines, entire neighborhoods, in competing directions. And once the rupture starts, it doesn't stop. Not until the fault decides it's done. This is where the real danger begins. The threat isn't a single segment failing. It's what happens when the rupture crosses segment boundaries. The literal cascade scenario. A continuous break that can run unbroken. From the Salton Sea, through the Carrizo Plain, and into the transverse ranges. Because the first seconds shape the next 2 minutes. The rupture direction, its acceleration, its ability to jump gaps between fault strands, all determine whether this becomes a magnitude 7 range quake, or something pushing into the high 7s and low 8s, shaking half a continent. And as that rupture races north towards cities built directly on the fault, the consequences accelerate with it. What happens when that moving break reaches them, and what it does once it arrives, is the story of the next section. Most people talk about the San Andreas Fault as if time is on our side, as if we're waiting for something far off, some hypothetical disaster the next century will deal with. But the truth is sharper than that. The southern segment of the San Andreas, running from the Salton Sea up toward the San Bernardino Mountains, has been locked tight since the late 1600s, more than 300 years without releasing major strain. That's not stability. That's silence under pressure. You've heard people say, the big one is inevitable. That's not wrong, but it misses the point. It's not inevitable someday. It's overdue. Now here's the detail buried in scientific papers. Not all parts of the San Andreas behave the same. The central segment, stretching through Parkfield and creeping up towards San Juan Bautista, slips steadily, almost too steadily. It releases strain at the surface in a slow-motion glide measured in millimeters per year. And ironically, that calm movement is actually protective. Every millimeter it slides is energy that won't be stored for a catastrophic rupture. But that steady creep creates a different kind of danger. It acts like a vice tightening around the locked ends. To the north and south, the fault isn't slipping at all. 2 massive blocks of crust, held in place not by stability, but by friction. Imagine a thick steel cable anchored at both ends. The center section glides smoothly, but the ends? They don't budge. That's where the strands begin to fray. And on those locked segments, the quiet years people take comfort in, they're not comforting. They're warnings. This leads to the question scientists debate behind closed doors. Does the creeping central section act as a barrier? A buffer that prevents a rupture from the south from cascading into the north? The best evidence suggests it might, acting like a speed bump that slows or stops rupture energy. But might isn't certainty, and faults don't follow human expectations. They follow physics. Here's where you come in. If you lived on a fault segment that was 300 years overdue, would you want quiet or information? Because satellites using InSAR technology now track the crust deforming around the locked sections. They show the land bending, literally warping, under accumulating strain. Like a surface trying to absorb a blow it knows is coming. This isn't a movie countdown. It's the slow winding of a physical limit. A limit that, once crossed, doesn't ask permission. When the locked segments finally rupture, the first seconds decide everything. A deep shear failure races upward and outward, and the fault unzips faster than you can blink, 2 miles per second, carving through rock that held its grip for generations. In the south, the rupture tears past the Salton Sea's geothermal maze. In the north, it races beneath the transverse ranges, snapping through the same compression-warped rock that once created them. What follows isn't one earthquake. It's a sequence of failures, each segment releasing centuries of stored stress. The ground begins to ripple in long, rolling waves, like the entire crust is breathing unevenly. Roads kink, rail lines twist. Aqueducts designed to carry half the state's water supply shear apart in seconds. And then comes the part people never expect. The shaking gets worse the closer you are to the fault, not the epicenter. For communities built directly on or across the San Andreas, Palisade, Desert Hot Springs, Wrightwood, this means violent, sideways lurches that arrive almost instantly. Cities farther out don't escape either. Los Angeles and the Inland Empire sit on deep sedimentary basins that behave like bowls of jelly. They trap seismic waves, amplify them, and release them slowly, stretching a few seconds of shaking into a minute or more. Buildings that survive the first shock face a second danger, the resonance that comes after. Some power grids trip instantly, others overload. Cell towers cascade into blackout zones. And because the southern San Andreas runs directly beneath critical junctions of the state's infrastructure, the break sends out consequences long after the shaking stops. Water shortages, transportation paralysis, and communications outages that can ripple for weeks. But in a way, all of this is simply the surface expression of something deeper. The Earth finally releasing stress it has been storing since before the United States even existed. When this system breaks, it doesn't negotiate. It resets.